We will now discuss the spectrum of a compact operator. In finite dimensions, given a matrix, the spectrum is just the set of all eigenvalues. In the infinite dimensional case, we saw several examples. You could have eigenvalues, you may not have eigenvalues. Spectrum consists of various things, all kinds of possibilities occur. Now we will study the case of a compact operator, which is more like the finite dimensional case. So more precisely, we have the following theorem. So let V be an infinite dimensional Banach space and let T in L of V be compact. Then A 0 belongs to sigma of T. B, every non-zero element of sigma of T is an eigenvalue with finite geometric multiplicity. What is the geometric multiplicity? It is nothing but the dimension of the kernel or null space of T minus lambda I. Okay, C. If lambda n is a sequence of non-zero eigenvalues converging to lambda, then lambda equal to 0. So in particular, the non-zero elements of sigma T, the spectrum, are all isolated. Because nothing can converge to them. Okay. D, one of the following alternatives holds. You can have sigma T equal to singleton 0, there is nothing else in the spectrum. 2, sigma T minus 0 is finite, and 3, sigma T minus 0 consists of a sequence of eigenvalues converging to 0. So one of these three will hold. Okay. So let us look at a proof of the statement. So we already saw that composition of compact maps is compact. Identity map is not compact in infinite dimensional space because the unit ball is not compact, and therefore you have that a compact operator cannot be So T compact implies T not invertible, and therefore this we have already seen, therefore 0 has to belong to sigma of T B. Okay. So now let lambda not be equal to 0, okay, and then you write T minus lambda I as equal to minus lambda I minus lambda inverse of T, and this is a compact perturbation of the identity. Therefore, the Ries-Fredholm theory holds, and consequently if n I minus lambda inverse of T is singleton 0, this is if and only if range of lambda I minus lambda inverse of T equal to the whole space V. So 1 1 if and only if on 2, and therefore implies in this case that I minus lambda inverse of T, and hence T minus lambda I is invertible. Therefore, lambda not equal to 0, lambda in sigma T implies n of I minus so T minus lambda I is not equal to singleton 0, and therefore implies lambda is an eigenvalue. And again, by the Ries-Fredholm theory, this dimension is finite, and therefore lambda has finite geometric multiplicity. So that proves B. So now let us prove C. So let lambda n be a sequence of distinct non-zero eigenvalues. Okay, then there exists un such that not equal to 0, such that T of un equals lambda n un. Okay, so claim un is linearly independent. The set of all eigenvectors of the distinct eigenvalues form a linearly independent set. Okay, so first singleton u1 is independent because u1 is not equal to 0. So assume u1 to un linearly independent. So if possible, let un plus 1 be written as sigma I equals 1 to n alpha I ui. Okay, that means it's not linearly independent. Since the first n are linearly independent and you're adding one, you make it dependent, that means the last new one is a linear combination of the previous ones. Okay, now you multiply both sides by lambda n plus 1, so sigma I equals 1 to n alpha I lambda n plus 1 ui equals lambda n plus 1 un plus 1, but that is T of un plus 1. So now you apply T to this, you get sigma I equals 1 to n alpha I lambda I ui. Okay, so this implies that sigma I equals 1 to n of alpha I lambda n plus 1 minus lambda I ui equal to 0. But you know u1 to un are linearly independent, and these are all not 0 because the eigenvalues are distinct. So this implies that alpha I equals 0 for all I, and that implies that un plus 1 is 0, and that's a contradiction. You cannot have an eigenvector which is un, our assumption is un, all the uns are non-zero. Therefore the uns are linearly independent. Okay, so now you set Vn to be the span of u1 to un. So this n dimensional subspace therefore closed. okay, and therefore we have an increasing sequence. We have V1 strictly contained in V2, strictly contained in V3, and so on. Vn strictly contained in Vn plus 1, and so on. Okay, so strictly containing sequence of closed finite dimensional, so finite dimensional, hence closed subspaces. So we now can apply the Rees lemma. You have a closed subspace, therefore there exists a Vn in capital Vn such for each n, such that norm Vn equal to 1 and the distance of Vn from V n minus 1 is bigger than or equal to any 1 minus epsilon. So we will take epsilon equals half. So for all n bigger than or equal to 2. Okay. So now let lambda n converge to lambda, which is if possible not 0. So then we will get a contradiction, and therefore lambda n has to only converge to 0. So you look at the sequence 1 by lambda n Vn is bounded. Why is it bounded? Norm of Vn is 1, lambda n converges to lambda not equal to 0, so it is bounded away from 0. So 1 by lambda n is a bounded sequence, okay, and therefore this is a bounded sequence. Okay, and also if 2 less than or equal to m less than n, what do you have? Vm minus 1 is contained in Vm, which is contained in Vn minus 1, which is contained in Vn. Okay, so this is because n is bigger than m, you have all these inclusions. Now let us look at 1 by lambda n Tvn minus 1 by lambda m Tvn. That is equal to 1 by lambda n Tvn minus Vn, or let me write it as 1 by lambda n bracket lambda n Vn, okay, minus 1 by lambda m Tvm minus Vm minus lambda m Vm, okay, plus Vn minus Vn. Okay, so is that okay? So 1 by lambda n Tvn, 1 by lambda n Tvm is there. This is minus Vn plus Vn plus Vm minus Vm. Okay, so this we have just added and subtracted. Okay, now you can look at Tvn minus lambda n Vn. Okay, what about this? So Vn can be written as sigma I equals 1 to n alpha I ui. Okay, so what is Tvn? Tvn is equal to, I just have to, so let me just take the last one, so that is alpha n lambda n un, okay, plus sigma I equals 1 to n minus 1 alpha I lambda I ui. Okay, and then Vn, lambda n Vn equals alpha n lambda n un minus sigma I equals 1 to n minus 1 alpha I lambda n ui. Okay, so if you subtract Tvn minus lambda Vn, these two get cancelled out, and therefore you have that this belongs to Vn minus 1. So we have that this vector is in Vn minus 1. Similarly, this vector belongs to Vm minus 1, and this of course belongs to Vm. So if you look at all of them, Vm, Vm minus 1, Vn minus 1, so this is the largest. So the entire thing belongs to Vn minus 1, and therefore we have 1 by lambda n Tvn minus 1 by lambda m Tvm is equal to Vn minus W, where W belongs to Vn minus 1, and therefore norm of 1 by lambda n Tvn minus 1 by lambda m Tvm is greater or equal to half by our choice, and this is a contradiction because 1 by lambda n tvn is a bounded sequence and T is a compact operator, and therefore it must have a convergent subsequence, and this has, so this implies that 1 by lambda n tvn is bounded and has no convergent subsequence, no Cauchy subsequence, therefore no convergent subsequence, and that is the contradiction to the compactness. So the contradiction is there. Therefore, this implies that lambda has to be equal to 0. So that proves the part C. Now D. Okay. So you look at, for every n in n, you take sigma t intersect mod lambda in lambda in C such that mod lambda is greater or equal to 1 by n. So this is a compact closed set, this is compact, so the intersection is compact. So if it's compact, it cannot, if it has an infinite number of elements, then there must be a convergent subsequence which should converge to something whose norm is bigger or equal to 1 by n. That's not possible by part C. So by C, this set is either empty or finite, and therefore this implies, since sigma t minus 0 is the union of all these sets, is either empty, finite, or consists of a countable number of elements. Okay, so if it's a countable number of elements, so you can number them as some sequence lambda n, which is in sigma t minus 0. Okay, so then you take any subsequence lambda n k. So that is still in the compact set sigma t, and therefore there exists a further subsequence lambda n k l which will converge, and that we just saw has to converge only to 0. So every subsequence has a further subsequence which converges to 0, and this implies that lambda n goes to 0. Okay, so this is a very beautiful topological fact, very useful, very trivial observation, but still. So in a topological space, given a sequence such that every subsequence has a further subsequence, if you like, which converges to the same limit. So whatever may be the sequence or subsequence you choose, the limit is always the same. Then the entire sequence converges to that limit. Just think about it, it's just a two-minute thing, and you can easily show that this, and it's very useful when you have convergence of a subsequence and you want to assert something about the convergence of the whole sequence. You show that the limit is independent of the subsequence chosen, and therefore the entire sequence will converge. So very useful topological tool. Okay, so now let us look at some examples. So T B to B. Okay, so if it's finite rank, then it is compact. So let us take T from L2 to L2. Okay, so Tx equals 0, x1, xn, then zeros. So I cut off at the n plus first term. So this is the n plus first place. So there I cut it off. Okay, so what is T square? So this will be 0, 0, x1 up to x minus 1 and then zeros. And if you do like this, T to the n plus 1 will be identically 0, and therefore it's a nilpotent operator. Hence 0, lambda equal to 0 is the only eigenvalue. And of course you can easily find an eigenvector where, for instance, En is an eigenvector. En goes to 0 or En plus 1 goes to 0, and therefore you have En plus 1, T of En plus 1 is 0, and therefore you have that lambda equals 0 is the only possible eigenvalue. So sigma T has no non-zero eigenvalues. It should all, and T has finite rank. Okay, T has finite rank and hence compact. So sigma T 0 must be in the spectrum, and 0 is the only eigenvalue, no other eigenvalues. So sigma T is just 0. Okay, so we have shown that that is possible. Okay. Next you look at again T from L2 to L2, and let alpha n be a sequence of complex numbers which go to 0. Okay, and then you define T in the following way: T of x equals alpha 1 x1, alpha 2 x2, alpha n xn, and so on. Okay, and you define Tn x, which is alpha 1 x1, alpha 2 x2, alpha n xn, and then zeros. Okay, then Tn has finite rank, and what can you say about Tnx minus Tx? This is equal to sigma I equals n plus 1 to infinity. So you have alpha I square mod xi square. And therefore that's less than equal to sup I greater than equal to n plus 1 mod alpha I square norm x square. Okay, so this means that norm of Tn minus T goes to 0 because alphas go to 0. So sup after some finite stage can be made as small as you please, because all the alphas must be less than or equal to epsilon after some finite stage, and therefore this goes to 0. So Tn has finite rank, and T is the limit of finite rank operator, so this implies that T is compact. So now let us see what happens. 1, no alpha I, so let me write it better, alpha I not equal to 0 for all I. This implies T is 1 1, implies 0 not an eigenvalue. Two, finitely many alpha I are 0 implies 0 is an eigenvalue with finite geometric multiplicity. Why? Because what is every alpha I, since alpha I eigenvalue with eigenvector ei for every I. So that is the reason why you get this. So now if you have 3, alpha I equal to 0 for infinitely many I. That means, let's say for all the odd alpha i's are 0 and the even alpha i's are non-zero and go to 0. Okay, in that case you have that 0 lambda equal to 0 is an eigenvalue with infinite multiplicity, infinite geometric multiplicity, then namely null space is infinite dimension. So you see, for the eigenvalue 0 we can say nothing. It may not be an eigenvalue as we saw in the previous exam. It may be the only eigenvalue that's possible, or it may not be an eigenvalue as we saw in 1, and it may be an eigenvalue of finite multiplicity or an eigenvalue of infinite multiplicity. Okay. So, if only finitely many alpha I are non-zero, then sigma t minus 0 is finite. 5. If infinitely many alpha I are non-zero, then sigma t minus 0 is set of all alpha I not equal to 0, which is infinite, and alpha I will converge to 0 because of our assumption, because it gives you a subsequence and therefore it has to go to 0. So, all the possibilities in statement D of the theorem have been are satisfied. So, final example, again you take t from L2 to L2 and then you take Tx equals alpha 1 x1 etc. alpha n xn and so on. Okay. So, then we saw that if alpha I goes to 0, then T was compact. So, alpha I goes to 0 implies T compact seen above. Now, if T is compact, each alpha I being an eigenvalue, we have alpha I tends to 0. So, because a sequence of eigenvalues, non-zero eigenvalues must converge to 0, and therefore we see that T is compact if and only if the alpha I's go to 0. Okay. So, this is about the general structure of the spectrum of a compact linear operator. Now, we will next look at compact self-adjoint linear operators, which are very special and have lot of applications, and that we will do next time.